Assalamualaikum and good morning. We are from Group 1. We will be presenting the process control on enzymatic processing in guava fruit juice production. These are our group members, Puteri Nur IZZAH, Lim Sini, Nur QASDINA, Nur ATMA FARINA, and Ng Tian Hui. Advancement in food processing technology have led to the implementation of process control where it is effective than traditional control methods. Enzymatic treatment in guava juice production improve extraction yield, juice clarity, and overall product quality. And this is where process control plays a main role in order to satisfy environmental and product quality standards while maintaining safe and cost-effective operation. So this study focused on process control, problem statement, control objective, process variable, mathematical model derivation, tuning and controller simulation on simulating stability, robustness, and AI involvement in guava juice production. This is the process flow of the guava juice production. First is receiving of guava fruit, where quality inspection will be done to choose the best fruit for production. The second process is washing to remove contaminants and dirt. The third process is peeling, where we remove the outer skin parts of the fruit as we only wanted to use the flesh. The fourth process is pulping to extract juice with the help of milling process. The fifth process is enzymatic treatment. This is the process that our group has chosen to do a process control analysis. Pectin in guava is broken down by pectinase, which reduces its viscosity and improve extraction yield. Here, we control the temperature at 43 to 45 degrees Celsius for optimum enzyme performance. The sixth process is filtration to remove impurities. The seventh process is evaporation to achieve desired concentration. The eighth process is pasteurization to eliminate microorganisms. The last process is packaging. Packaging of guava fruit juice in glass bottles or paper plastic and labeled before ready to be distributed.
Next, moving on to the problem statement, our control variable is temperature of the mixture. Why? Because enzymes are highly sensitive to temperature changes that can impact their activity and their efficiency. Therefore, controlling temperature helps maintain the stability and activity of enzymes. Next, our manipulated variable is heat energy supply from the heating coil. Since excessive heat energy can denature enzymes and impair the juice extraction process, therefore manipulate the heat energy provides the necessary kinetic energy for enzymes to function efficiently.
Next, I'm going to explain our control objectives. There are basically 7 of control objectives, namely safety, environmental protection, equipment protection, smooth operation, product quality, profit, and monitoring and diagnosis. However, we are only going to focus on 2 of them. First is smooth operation. The objective is to ensure smooth and continuous production process. As control measures, we will monitor and control production parameters to prevent disruptions. By monitoring heat energy supply to the heating coil, that is the manipulated variable, we can ensure that the smooth operation of guava juice during the enzyme treatment process. Next is product quality. Our objective is to ensure that each batch of guava juice consistently meets predefined quality standards regarding taste, color, aroma, and texture. In this case, it is to ensure the activation of enzyme pectinase to react with the guava juice. This can be controlled by doing regular testing and analysis of key quality parameters such as sugar content, acidity, pH, temperature, and flavor profile. By controlling the optimum temperature, which is our controlled variable, that is required of 43 degrees Celsius for the pectinase to activate, we can ensure that the enzyme treatment process is a success and ensuring the product quality at the end.
Now I will present about process variables for our project. CV is temperature of the mixture, NV is heat energy supply from the heating coil, while disturbance is temperature of the surrounding.
Before starting to build a mathematical model, there are a few assumptions that we need to make. So mostly important is assume this process is a batch process, and the following assumptions you can read by your own. So after the assumption, we can perform overall energy balance. As you can see on the screen, the small change of temperature is equal to temperature inlet minus temperature outlet, and plus the the heat from the heating coil, and the process is assumed to be as in steady state, so small change of temperature is equal to 0. After performing the Laplace transform, then we can factorize the TO prime S, and then we can start dividing the CP omega to make it into in the transfer function form. By comparing to the first order transfer function, we can know that tau is equal to rho v over omega, and k, the gain, the process gain, is equal to 1 over CP omega. After that, we can insert some relevant data into the first order transfer function. The heat capacity and the density can found from the journal about enzyme treatment, whereas the volume and the flow rate we just assume only.
For our PNID diagram, it consists of a mixing tank that will mix a guava substrate with the enzyme pectinase. And since our CV is to control the temperature of the mixture, so we put a thermocouple as a sensor in the mixture, and then it will measure the temperature and it will send the signal to the transmitter, and the transmitter will convert the signal from the thermocouple and into a standard instrumentation signal to the temperature controller. And if the temperature of the mixture in the mixing tank is away from the desired temperature, the controller will send a signal to the heating coil to control the temperature of the mixture to the optimal temperature.
Before checking the stability, we need to make a few assumptions first. First, the GB and GM are equal to 1, so the GP will be our transfer function, while the controller transfer function, GC, will be the Ziegler-Nichols tuning method, the values that we gain from the try and error from the simulating. Then we apply the respectively data into the characteristic equation, and finally we can obtain the quadratic equation from the working. So using the Ralph-Hurwitz method, we put the value into the respective column according to the route array, and we get the B1 value is positive. Since all the values in the first column are positive coefficients, so the system is stable.
In the robust simulation, we will increase the value of proportional gain 25% from the initial value and also decrease for 25%. This method aims to check on the performance of our process. This table has shown our robust simulation calculation from our Ziegler-Nichols best tuning method. These are the graph for the value with initial proportional gain, increase 25% and decrease 25%. When we decrease the proportional gain, it takes longer time to stable and we obtain value that is more than the desired set point. While we increase for 25%, we can see an overshoot occurrence that indicates potential instability. It also has lower rising time compared to the initial proportional gain. It may be good but has risk to overshooting like this system. That is to say, we can imply that our system unable to withstand the 35% of error range, thus leads to instability in gaining the desired output in tuning process. Previously, Rothe-Hurwitz test system stabilities in nominal or ideal conditions, but it appears unstable under external disturbance. Gain scheduling can address low robustness under real-world disturbance by adjusting gains based on operating conditions. Gain scheduling allows smooth transition between predefined control parameters, enabling effective management of uncertainties and disturbance in real-world applications.
We are going to continue with the improvement that will achieved by utilizing artificial intelligence in enzymatic treatment. The application of AI, specifically the artificial neural network, comprises an input layer, hidden layer resembling the neural network of the human brain in terms of information processing. With AI, the fermentation efficiency can be boosted by having a time-dependent control strategies. Time is treated as an input in ANN models, while a genetic algorithm optimizes fermentation parameter control trajectories. Also, we have learning analytics. It can be done through collecting and monitoring data from various stages of the enzyme treatment process, including raw material quality, enzyme concentrations, temperature, pH levels, and other relevant parameters. This real-time data collection provides a comprehensive view of the process. In addition, by implementing feedback loops based on learning analytics enables a dynamic adjustment of process parameters. As the system learns from historical data, it can provide real-time feedback to control systems, ensuring optimal conditions during enzyme treatment.
Based on tuning control systems in Simulink, different methods can be used to determine the controller parameters. In this case, we have used three tuning methods which are Ziegler-Nichols, ZN, ITAE, and Amigo. Based on diagram 8.1, it shows that using the ZN method has the stable graph because it is nearest to our set point. On the other hand, based on diagram 8.3 and 8.4, the Amigo and ITAE method showing its higher gains that may result in a more aggressive response and potentially exceeding the desired set point more than true. The ZN method uses trial and error to find the values of Kc, Ti, and Td that provide stable and satisfactory control performance. On the other hand, by using the ITAE method, we obtain the value of Kc from mode P and value Ti from mode I and value Td from mode D. Calculation using the ITAE method is by using the formula from the table at appendix. Next, we use another method to compare this tuning, which is by using Amigo. This method is similar to ITAE, where we use formulas to find Kc, Ti, and Td. The table that we refer to can be found in appendix. Based on this table, the ITAE and Amigo Kc value is too high that can lead to overshooting and instability. The Td value is also too high that can amplify noise and lead to instability. Therefore, the ZM method is the best method in this case. After obtaining the value of Kc, Ti, Td from the ITAE and Amigo method, we need to convert the value into Kp, Ki, and Kd by using the PID equation where Kp is equals to Kc, Ki is equals to Kcti, Kd is equals to Kctd. Furthermore, a PID controller can often achieve better performance compared to a PI or P controller. The inclusion of the derivative term in the PID controller provide additional benefits in terms of system response and stability. ITAE method may result in higher overshoot compared to the ZM method, in which the ITAE method tends to result in higher proportional gain Kp and intergain Ki value. Higher gains can lead to more aggressive contraction, which can cause the system to overshoot the desired set point. Therefore, the ZM method is suitable for this case.
Conclusion, we choose enzyme treatment as the main process because it helps to increase the yield of the juice in the extraction process. So we develop a dynamic model with a reference from literature and research. Since the temperature is the most important for the enzymatic activity, therefore a temperature controller is used in a PNID system, and a closed loop circuit is designed to control the temperature of the mixture with the heat supply. And then we also find the transfer function of the model, and then the tuning method we use are ZN, ITAE, and Amigo method. And then the best tuning method is ZN because it provides more satisfactory performance across a wide range of systems. After that, we also conduct a stability test using the row array method since all the coefficients in the characteristic equation are positive. After computation, we've discovered that all entries in the first column of row array are positive, indicating that the system is stable. Lastly, a robust test was applied to check the system under conditions of a higher and a lower happy, and it shows an unhealthy system for both conditions.
That's all from us. Thank you.